Okay. Hi, everyone. I should say everyone on the YouTube because people haven't joined. That's fine. I teach it. I think, yeah, that's fine. So just I do it for my love for mathematics. That's fine. I do it. I teach it for myself. So I try to enjoy the math myself. So here I'm gonna talk about uniform manifold approximation and projection, or UMAP in short. So what is that? It's one of the state-of-the-art methods for data visualization. We talked about TSNE, which was a data visualization method. Now I'm going to talk about UMAP. UMAP came after TSNE, and it is kind of one of the state-of-the-art methods for data visualization, which is competing with TSNE. And both TSNE and UMAP have been used for data gene expression visualization as well. So first off, let's talk about data graph in the input space. So as I said, uniform manifold approximation and projection, or UMAP in short, it was proposed in 2018, which is not very far away from us. Okay, consider a training data set X, which is D by N, where N data points, each of which is D-dimensional. N is the sample size or the number of data points, and D is the dimensionality. We construct a k-nearest neighbors graph or KNN graph for this data set. Okay, and it has been empirically observed that UMAP requires fewer number of neighbors than TSNE. So that's one of the advantages of TSNE, and its default value is 15. So we take 15 number of neighbors, and we denote the jth neighbor of xi by xij. So xij denotes the jth neighbor of xi. Let ni denote the set of neighbor points for the point xi. So ni is a set of xi1 until xik, right? Okay. And we treat neighborhood relationship between points stochastically. So it's, in this sense, it's similar to TSNE, right? Because it treats the neighborhood relationship between the points stochastically and probabilistically. Inspired by SNE and TSNE, we use Gaussian or radial basis function kernel. Okay, so we use it's, in this sense also it's similar to TSNE, but we'll see the difference. We use Gaussian or radial basis function, RBF kernel, for the measure of similarity between points in the input space. What do I mean? Every point has a Gaussian distribution around it, which shows the probability of other points to be its neighbor. So the closer the points to that point, the more probable they are the neighbor of that point. The farther away they are, the less probable they are neighbors. The probability that a point xi has a point xj as its neighbor can be computed by the similarity of these points, right? So pji, what does it mean? It denotes that the probability that point xi takes or accepts point xj as its neighbor. Okay. Then if xj is in one of the k nearest neighbors of xi, then we take this as this Gaussian distribution as a probability of being neighbor. Otherwise, we set it to 0. So here is one of the differences. SNE used a Gaussian distribution for all of the points. However, here we are using Gaussian distribution only for k nearest neighbors. And here, this denotes L2 norm. And as you see, this is the format of Gaussian distribution. So here we have minus rho I And this rho I is the distance of xi to its nearest neighbor. So rho I, we denote it as minimum of L2 norm of xi and xij for all j from 1 to k. So it means that this is the distance of xi to its jth neighbor, Euclidean distance. And we calculated this for all of the k neighbors, and we take the minimum one. So this is the minimum distance. And why do we do that? Because we want kind of to normalize this. That's the reason we have minus rho I in the numerator, because we want the smallest distance to be 0, right? In this numerator of this Gaussian distribution. Okay, therefore for the nearest neighbor, when this becomes 0, e to the minus 0 becomes e to the 0, which is 1. And it means that for the smallest distance, this becomes 1, right? And you notice that this pji, it doesn't sum to 1, right? It doesn't sum to 1 because we don't have a normalization factor before this exponential operator. But at least it behaves like probability, but it doesn't necessarily sum to 1. Okay. Then sigma I is the scale parameter, which is calculated such that the total similarity of point xi to its k nearest neighbors is normalized, right? So this sigma I, what was that? It was, do you remember? Here we had it. This is the variance, right? Or standard deviation, doesn't matter. The variance in the Gaussian distribution. And how can we find that? Do you remember? We also had the same idea in Tisny and SNE. We can use binary search. So what do we do? Consider equation 3. We use binary search to find out which sigma I satisfies this equation. Why? Because we want the total similarities. This is total, right? The total similarity of point xi to its k nearest neighbors to be normalized. Okay. And how can we do binary search? What do I mean by binary search? For example, you know what is the maximum upper bound for sigma I? Assume it is 100. And we know the smallest one maybe is 0, right? Because it's a non-negative parameter. Then, for example, we consider 100 and see how much it is above logarithm of k. Then we halve it. Then we consider 50. Then we see whether we became less than logarithm of k, or we are still above logarithm of k. If we are still above logarithm of k, then we halve sigma I again. It becomes 25. Otherwise, if it has become less than logarithm of k, we go to the second part, which we halve the second part, which therefore we go and set sigma I to 75. So we can play around with the ranges, and in each iteration we choose that part and we halve it until convergence of sigma I. Okay, if you have passed my optimization course also, or have seen that on YouTube, you will see that it's very related to Newton-Raphson method, which inspired Newton's method for optimization. Okay. Note that Tisny has a similar search for its scale or for its variance using entropy as perplexity. So Tisny uses another equation for this binary search, but they both are defined in sigma using binary search. These searches make the neighborhoods of various points behave similarly, because the scale for a point in a dense region of data set becomes small. The scale of point in a sparse region of data becomes large. Why are we finding this sigma I by binary search? For this reason, because the density of data set differs in different parts of the space. Therefore, in denser areas, the sigma should be smaller because the variance is smaller. But in sparse regions of data, then the sigma should be large. Okay. In other words, UMAP and Tisny both assume or approximate that points are uniformly distributed on an underlying low-dimensional manifold. By finding this sigma, we are trying to assume that the density of the data set is kind of uniform, Okay, so we are canceling the effect of density in the data set by this binary search. And I think now you understand why UMAP is called uniform manifold approximation and projection. Uniform in the title of UMAP is because of this reason, right? Okay. Equation 1, do you remember this was equation 1? I'm repeating it here. Is a directional similarity measure. What does it mean? It's not symmetric, it's asymmetric. To have a symmetric measure with respect to I and j, so I want pj given I be equal to pi given j. What should I do? We can symmetrize it in this way. So pij or pji, this is symmetric, is defined as pj given I, which is defined here in equation 1, plus pi given j, so you change the I and j here in this equation, minus pji times pij. Okay, and I think you will understand easily in equation 4, if you change I and j, you will see it will remain the same. This is a symmetric measure of similarity between xi and xj. Do you remember in symmetric t-SNE, in symmetric SNE, also in t-SNE, we made it symmetric in another way. We said pj given I plus pi given j divided by 2. But now they are using another formula. It doesn't matter. As long as we can make it symmetric, that's fine. Okay. So data graph in the embedding space. Let the embeddings of the points be y, y1 to yn. And so what do I mean? So I'm denoting the embedding because I want to find embeddings, low dimensional embeddings of the data points, right? Assume the ith data point is xi. Then what happens? So assume that ith data point is xi, its embedding I denoted by yi. And I assume the dimensionality of input space is d-dimensional, but embedding is p-dimensional. P is the dimensionality of the embedding space. And it is usually smaller than d, much less than d usually. For visualization, the p should be either 2 or 3, right? Note that yi is the embedding corresponding to xi, right? Okay. In the embedding space, the probability that the point yi has the point yj as its neighbor, right, can be, we define it to be this. Okay. So here we don't use Gaussian distribution anymore in the embedding space of UMAP. Similar to the idea of t-SNE. Do you remember in its embedding space? I think in t-SNE, in its embedding space, yes, we used student t distribution, but in its input space, we used Gaussian distribution, right? Similar here, in its input space, we use Gaussian distribution, but in embedding space, we use this equation 5 as a probability. That what is this? The probability that yi and yj are neighbor of each other, and it's symmetric. It's symmetric with respect to I and j. Okay. Here we have several variables, a, b. They are greater than 0. These are hyperparameters determined by the user. You can find it by cross-validation. By default, we usually use a equal to 1.929 and b equal to 0.7915 according to reference one. Although it has been empirically seen that setting a to b to 1, if you set a and b to 1, doesn't qualitatively impact the results. So the results don't change much if you set a and b to 1. Okay, so optimization cost function. Now, so far we defined the probability distributions in the input space and in the embedding space. Now, optimization cost function. UMAP aims to make the data graph in the low dimensional embedding space similar to the data graph in the high dimensional embedding space. So the idea of UMAP is this. I have a graph of data in the high dimensional input space. Let me embed data in the low dimensional embedding space in a way that the data graph in the embedding space becomes very similar to the data graph in the high dimensional input space. Okay, in other words, we treat equations 4 and 5 as probability distributions, right? And minimize the differences of these distributions. So similar, we do it a lot. We did it also in S23. But as you see, the formulation of distributions differ. Also, their cost is a bit different. So in SNE and TSNE, we use KL divergence. However, here we use fuzzy cross entropy. Although there is a relation between KL divergence and cross entropy, but it's a bit different. It's a bit different. Okay. So what is this? This is a cost or loss function in UMAP. So we have double summation, right? Why? Because we have pairs of points, right? So we have double summation, and we have Pij, natural logarithm of Pij over Qij plus 1 minus Pij, natural logarithm of 1 minus Pij over 1 minus Qij. Ln here is a natural logarithm. Okay, this is called fuzzy cross entropy. The definition of cross entropy is in the field of fuzzy category theory. So category theory is one of the fields in mathematics, right? In pure mathematics, I think. Category theory, if for more information, you can see our tutorial paper. We have a bit talked about category theory and fuzzy category theory in that tutorial paper on our UMAP, and the name of tutorial paper is Uniform Manifold Approximation and Projection, in parentheses UMAP, tutorial and survey. Okay, now let's discuss this cost function. The first term in equation 6, the first term here, it is attractive force, and the second term is the repulsive force. So what does it mean? The first term tries to attract similar points to each other in the embedding space, but the second term, which is repulsive force, it pushes away the dissimilar points in the embedding space. Okay, so why? But why is the first term attractive force? Let's see. It attracts embeddings of the neighbor points toward each other. This term should only appear, this is the reason why it's attractive force. This term, the first term, should only appear when Pij is not 0, right? Here we have Pij. So when Pij is not 0, then we have the first term, which means that either xj is a neighbor of xi or xi is a neighbor of xj. Do you remember? Why? Because of this reason. Let's go back to what we had. Because of this. If it's not in the k-nearest neighbor, it becomes 0, right? So that's the reason. When they are neighbor of each other, the first term appears. Otherwise, it's 0. And hence, it tries to attract them. It appears when they are neighbors. And why does it attract them? Can you tell me? So this is because here we are trying, this is cross entropy between Pij and Qij, right? We want Qij to be similar to Pij by minimizing that. Therefore, when Pij, for two neighbor points, we have them, and Qij, we try to make Qij similar to Pij by pushing Yi and Yj toward each other. So they become similar to each other as they are in the input space. Okay. The second term in equation 6, the second is repulsive force. So what does it do? It repulses the embeddings of non-neighbor points away from each other. Why? Because we have 1 minus Pij here. When does it appear? When Pij is 0. It means when they are not k-nearest neighbors of each other. Then we'll have the second term. And as you see, in the second term, I want to make, it is also a cross entropy form, right? I want to make 1 minus Qij similar to 1 minus Pij. So in other words, I want to make Qij similar to Pij, right? And but for non-neighbor points. And we know that Pij for non-neighbor points is small, therefore Qij should become also small. Therefore, they should be pushed away from each other. Okay. As the number of all permutations of non-neighbor points is very large, right? So we for similar points, we have a few number of similar points, but for non-neighbor points, we have a huge number of permutations. Then we use a technique which we also talked about it before in the course, called negative sampling. We talked about it in the lecture of let me think. I think in deep learning course, I talked about it in the lecture of restricted Boltzmann machine. So UMAP uses negative sampling. And what is this? This is a good technique, an important technique in machine learning. It says, rather than in every iteration, rather than telling the model, you should learn that these two are not similar, these two are not similar, these two are not similar. And I show every two non-similar points to it, then it will be overwhelming for the model and its complexity will be high. Rather than doing this, in every iteration, I just show one or a few pairs of non-similar points. And hopefully, after several iterations, when it sees different pairs of non-similar points, it will learn what we want it to learn, right? And that's called negative sampling. So we are sampling from the negative points or from the negative pairs. Okay, for every point xi, m points are sampled randomly from the training data set and treat them as non-negative or negative points for xi. Okay. As a data set is usually large, right? M is much less than n. The sample points will be actual negative points with high probability. So in negative sampling, we don't check whether the sample points are actual negative or not. But as the sample size is much less than the number of data points in the data set, with high probability, then they will be negative samples, right? Because it will be with low probability that we find positive samples by sampling them. So this is what the cost function of UMAP that we talked about. The summation over the second term in this equation is computed only over these negative samples. So this, I mean, right? So for positive points, which is the first term, we can consider all of the pairs of positive points. But for second term, which is considers the negative points, then we don't need to do the whole second loop. Otherwise, the time complexity will blow up. Then what do? We do negative sampling. Okay. Then UMAP, what does it do? It changes the data graph in the embedding space to make it similar to the data graph in the input space. So assume we have a data graph in the input space. We also, for the sake of optimization, we randomly initialize some graph in the embedding space. Then we change this graph in the embedding space so it becomes similar to the graph in the input space. Okay. Equation 6 is the cost function, which is minimized. This last function, it is minimized in UMAP. And the optimization variables are the embedding points, right? So let's minimize this cost function with respect to these embedding points. Then what happens? This should be bold, right? Okay. Okay, so here Pij is independent of the optimization variables yi. Why? Do you agree? So yi's are the embedding points, which are the optimization variables, right? However, Pij just shows the similarity, the probability of similarity between points in the input space. So Pij is not related to yi. Therefore, as the optimization variable is yi, I don't care about this term. This is a constant, right? Why can I drop it? Because the cost is not important to me, but the argument of optimization is important to me, so I can drop it. And let me think. Also, this term, this is also purely based on Pij, so I can drop it. Therefore, I will have only these two terms. I factor out the negative minus here, and I will have them here. This should be minimized. Okay, so this is what we had. I'm repeating it here. The two important terms in this cost function are what? We have minus logarithm of Qij. So this is logarithm of Qij, and this here is the minus, right? And we also have minus logarithm of 1 minus Qij. So this is this and the minus here. So I define this minus logarithm of Qij as Cija and minus logarithm of 1 minus Qij asCijr. Why? A stands for attraction or attractive, R stands for repulsive. So because equation 8 attracts the similar points to each other. Why? Because I have Qij, but also here we talked about it. We talked about repulsive and attractive forces just a few slides ago. But this second term, logarithm of 1 minus Qij, is for corresponding to non-similar points. Therefore, it's repulsive, right? Therefore, if we put these two equations 8, 9 into this equation, then we can rewrite the cost as this, as equation 10, right? And we know that, what do we know? We know that Pij and Qij, so we have Qij in these, and also Pij is here. Both Pij and Qij are symmetric with respect to I and j. Therefore, I can, rather than having the whole summation of j from 1 to n, where j is not equal to I can only have one of the triangles in this matrix. So I can say j from I plus 1 to n, because if I calculate Pij, I don't need to calculate Pji for that. Equations 8 and 9 are, so here equation 8 is attractive force and equation 9 is repulsive force. Attractive force attracts the neighbor points toward each other in the embedded space, while repulsive force pushes the non-neighbor points away, right? Okay. According to equation 10, this equation, Cija occurs with probability Pij. Do you agree? Here we have it. Also, Cijr, repulsive force, occurs with probability 1 minus Pij. I think correct. Okay. For every point, we call it the anchor point. So here the idea is similar to triplet loss. If you have seen, for more information, see my SIMES network, my lecture on SIMES network in deep learning course. Okay, I introduced triplet loss as for deep learning, but here we also have the same idea here. So we have triplets of anchor, positive, and negative. Anchor point, positive point, and negative point, where anchor and positive are similar, but anchor and negative are different, dissimilar. So the attractive force pushes the positive point toward anchor, and repulsive force pushes the negative point away from the anchor, right? And the attractive force occurs with probability Pij, and repulsive force occurs with probability 1 minus Pij. Okay. And by the way, as you see, if attractive force is occurring with probability Pij, therefore positive and anchor, if they are very similar to each other, Pij peaks, right? if I and j are close, similar to each other in the input space, then Pij is large. Therefore, this makes sense that Cij should happen with probability Pij. But if I and j are dissimilar, Pij is small. Therefore, Cij attractive force should be multiplied by a small number, right? Because they're dissimilar. Also, the same analysis holds for repulsive force. When Pij is large, when I and j are similar, Pij is large, 1 minus Pij is small. So the repulsive force should be multiplied by a small number. However, when I and j are very dissimilar, Pij is small, 1 minus Pij is large. Therefore, repulsive force should be multiplied by a large number. Training algorithm of UMAP. So here is the UMAP algorithm. We have input data, training data, x1 to xn. We construct a k-nearest graph, right? K-nearest neighbor graph in the input space. We initialize the embeddings y1 to yn by Laplacian eigenmap. So we can either, because it's optimization, right? An iterative optimization. Therefore, we have to initialize the points, embeddings. But they have empirically found out that it's better, easier for optimization to initialize it by one of the dimensionality reduction algorithms named Laplacian eigenmap. Okay, we didn't have time to go through Laplacian eigenmap in this course, but that's one of the algorithms for dimensionality reduction. For more information on Laplacian eigenmap, you can see my tutorial on Laplacian eigenmap. It's called, let me see, what was it called? It's called Laplacian-based dimensionality reduction, including a spectral clustering, Laplacian eigenmap, locality preserving projection, graph embedding and diffusion map, tutorial and survey. Okay, so this is the name of our tutorial. And also you can see the chapter of Laplacian-based dimensionality reduction in our textbook. Okay, so as I said, we initialize it by Laplacian eigenmap, and then we calculate Pij and Qij for all I and j from 1 to n, right? Why? So Pij can be calculated. Why? Because we have xi and xj. Qij also can be calculated because we initialize yi and yj, right? So we can calculate it. And here we initialize the variables eta and nu. Nu here is an iteration index. And eta, I think, as far as I remember, eta is a learning rate. Okay, so here, epoch index or iteration index, I increase it. Then I go to the for loop for, so these are the 2 for loops that we had in the cost, the 2 summations, right? And then here, I sample a uniform variable between 0 and 1. U here, big U stands for the continuous uniform distribution between 0 and 1. So you will be a random value between 0 and 1. If it is less than Pij, it means that Pij has happened. If it is greater than Pij, it means that Pij doesn't happen. So basically, for saying that if we have a probability Pij, we want to implement it in coding in computer. One technique is this: we sample a uniform variable between 0 and 1, and we have the value Pij. If it is less than Pij, so it means that it has happened. Otherwise, no, it hasn't happened. Okay, then we have if this has happened, then we update yi and yj by gradient descent, right? Where we have these derivatives. We will see these derivatives, okay? And then for n iterations, so for n, so what am I doing here? This is attractive, of course, for similarity, right? For similar points, we are doing this, but here, this last form is for negative sampling or repulsive forms, right? For m iterations. Why? Because m, rather than saying for all of the pairs of negative points, I'm only considering m of them. Then I calculate these two. So basically, for attractive forces, if Pij, if xi and xj are neighbors, I can update the embeddings of yi and yj based on their attractive force. Note that these are ci and ja, these two. Okay. But these two are derivatives of Cijr, repulsive force, with respect to value. Okay. You should note that. Also, I want you to understand this. First off, what am I doing with this if? I'm saying that if, do you agree, if 2 points are similar to each other, Pij is big, therefore it's more probable that I go inside the if. Therefore, it makes sense that I update them with an attractive force. If they are dissimilar, Pij is small, it's less probable that I go inside the if. Therefore, I don't do the attractive update. However, here we are saying that only if the 2 points are similar to each other, I update their embeddings, both yi and yj, and also for xi or yi, I consider m negative points. M negative points, and I update the yi and yl. L here is for the number of negative points, right? I do that, I update them. You should note that the original UMAP didn't update UL, because if we have a pair of similar points, I can update the embeddings of the pair. If I have a pair of dissimilar points, I can update the embeddings of the pair again, right? However, for the original UMAP, updated the similar, both embeddings of the similar points, but for dissimilar points, it updated only one of them. Doesn't matter. But I'm saying that we can update both of them again. Okay, we do it for all of the iterations until convergence, and in each iteration of convergence or in each epoch, we also decrease the learning rate. Why? This is exactly the idea, because in optimization, we usually start with a bit larger learning rate or step size, because initially we assume that we are away from the final solution. But when we get closer to the final solution, the learning rate should be decreased. And finally, we return the embeddings. Right? Okay. Training algorithm of UMAP. As this algorithm shows, a k-NN graph, k-nearest neighbor graph, is constructed from the training data, x1 to xn, right? So I think here I have explained the algorithm, but let me tell you some important things here, and because I have explained most of it. So here we are using a stochastic gradient descent, right? We saw that. Also, we are considering anchor, positive and negative points. Here we are sampling a uniform value for modeling Pij, right? Also, we are considering negative sampling. And as I said, in original UMAP, for negative samples, it only updates one of them, but we can update both of them. Okay, so we had these two. Do you remember? These were attractive and repulsive forces. The gradients of attractive and repulsive cost functions in UMAP are these. So derivative of Cij with respect to yi, it can be written as 2ab L2 norm of yi minus yj, right? Their embeddings, a squared, and also to the power of b minus 1. So to the power of 2b minus 1. And b, a and b are parameters. Do you remember we had these parameters in the Qij? Also in the denominator, I have 1 plus a, again, L2 norm of yi minus yj to the power of 2b times yi minus yj. So these is a scalar, right? But this is a matrix. And as you see, as expected, this is a p-dimensional vector because it's a derivative of a scalar with respect to a p-dimensional vector with respect to yi. Here also, I have derivative of Cij repulsive cos with respect to yi. Again, this is a scalar, and this is a vector, right? And it makes sense. Why? These two equations make sense. Why? Because finally, let me think a bit. Yes. So when yi and when 2 points xi and xj are similar, what happened? What happened? Both. Let me think. No, I wanted to say something, but I think what I have in mind is a bit wrong, so I don't want to say something wrong. That's fine. I think I haven't, I'm not sure whether I have provided the proof here. Oh yeah, I have. Okay, so we will prove these two equations. Okay, but also, why do we have epsilon here in the denominator? Because we don't want to have division by 0. If yi and yj are close to each other in the embedded space, then L2 normal of yi and yi minus yj becomes very small. So this becomes almost 0. This becomes almost 0, right? But this becomes almost 1. Doesn't matter. But this is multiplied by this term. So this term, if yi and yj are close to each other, this becomes almost 0. Therefore, I have plus epsilon in the denominator for the sake of the stability. And now, so let me think here. Oh, okay. What is the difference of these two equations and these? Here, these are derivatives of these Cij, A, and R with respect to yi, but these are with respect to yj. Okay. Well, the only difference is that here I have yi minus yj. For example, here I have yj minus yi, right? You can see that. Okay. So let's prove that. Well, what did we have? We had these two attractive and repulsive forces, and we also had these Qij, right? This is the probability of neighborhood in the embedded space. Now, for the first equation, which was the derivative of attractive force with respect to yi. So we can do it chain rule. Okay, chain rule. So we can say derivative of attractive force with respect to Qij times derivative of Qij with respect to yi. Okay, so here this is Cij minus logarithm of Qij. So its derivative becomes minus 1 over Qij, right? So what about derivative of Qij? Here it is with respect to yi. If you calculate this derivative, it becomes this. Let's see why a bit. Let's analyze it. So what is this? 1 over 1 plus a 1i minus yj. This, right? What is the derivative of fraction? Denominator becomes to the power of 2. This is exactly what we had. And in the numerator, I have derivative of numerator times denominator minus numerator times the derivative of denominator. Do you remember? This is the formula for derivative of fraction. So exactly, derivative of numerator times denominator becomes 0 because numerator is constant. Minus numerator times derivative of denominator. And this is exactly derivative of denominator. What is the derivative of denominator? So 1 is constant, goes away. And then I have these two, so I have 2b is a power, right? 2b, so I can say 2ab times this yi minus yj. Also, I reduce the power 1 with 1. Okay, so we saw that. Now what do we have? According to equation 5, what was equation 5? This qij, the equation 5 was qij, so we had it. Sorry, I came back. Okay, so this is equation 5 that we had. Interestingly, I can write it in this way. Let me think. So here 2ab is this 2ab, right? Here I have this exactly here. I have repeated it here. I have yi minus yj here. I have repeated it here. Put it here. I have, let me think. Oh, okay. We had this 2ab qi 2b. I've forgotten what happened here. Hi. I have forgotten what happened here, but I think as far as I remember, so here we have this term, right? We have this term in the denominator also to the power of 2. Therefore, the denominator is kind of qij squared. But why this is simplified to this currently, I can't find out. I need to concentrate on that. Let me think. Yes, that's correct.
The power is 2b minus 1, and in the denominator power is 2b.
Where is 2b minus?
In the numerator.
We have 2b minus 1?
It's the same, like b minus 1.
You mean here, right? You mean here? But the denominator is 1 plus a yi minus yb, right? No, there. I remember there was something I have forgotten. I wrote this tutorial 2 years ago. Let me remember what was happening here. But that's fine. Let's not stop here. According to this formula, apparently we can reach from here to here. If you find out, let me know. Otherwise, there is a reason. I didn't make it up. So I can say that here the power just, we should note that the power has become 1 here, and the power here is 2.
The power actually same as the below equation you starting with.
What?
First equation and second equation are different.
Which equation?
For first equation we have like 14 and 15.
Oh, sorry. I forgot this 1 minus qij. I forgot this 1 minus 1 minus 1 over. Sorry about that. Yeah, I got. Yeah. Sorry, I just forgot. Okay, so let me clean it a bit. Sorry if I made you confused a bit, but let me clean it. Just visually, I didn't see that term. Okay. So here I have qij. Also, what is this? According to equation 5 here, it is, you can write it as 1 plus a yi minus yj to the power of 2b to the power of minus 2, right? I bring it to the numerator, minus 2. This is 2 here. Okay, but this is equal to, according to equation 5, qij to the power of 2. I have minus 1 over qij, and I have qij to the power of 2. So these two cancel each other. Therefore, I will have 1 qij, and qij is 1 over this term, which is here, right? And the rest of the terms are as, sorry, okay. So we found out what has happened here. Okay, now for the second equation. So we just, I think we proved the first equation, right, which is equation 12. We proved that. Now for equation 13, derivative of repulsive force with respect to yi. By chain rule, I write it as derivative of Ci repulsive force with respect to Qij times derivative of Qij with respect to Yi. Then, okay, according to this equation, derivative of repulsive force with respect to Qij is 1 over 1 minus Qij for the derivative of logarithm, right? And also here, with the same explanation that I talked about here for this, the derivative of Qij with respect to Yi here is this, right? It's just the derivative of a fraction. And then what do we have? So here I have this term here. I have this term in the denominator here. I have this yi minus yj here. I have this term appeared here. I also have minus 1 to ab here, right? We just proved equation 13. Did we prove that? No. No. There is still some other steps left. Sorry. Equation 5. This was equation 5, right? The term in the numerator, so this term here, the term in the numerator can be simplified further. So this is term that we had, minus 2ab, L2 normal of yi minus yj to the power of 2 times b minus 1. So how can we simplify that? Because I have the power of 2b minus 2, right? So 2b is here, minus 2 is here. Agreed? Okay. Then, so I wrote it in this, I broke this into two, multiplication of 2 terms. Then, according to equation 5 again, according to this equation 5, I can write it as this. So this term here inside can be written as Qij inverse it can be written as Qij inverse minus 1, right? And so this term, it can be written as this. Now the term in the denominator, this is a term which we had in the denominator. Yeah, here it is. Okay, so I can simplify it according to equation 5. It is just 1 minus Qij, which is here. And what is this? Qij to the power of minus 2, right? And just multiply the terms to each other, it becomes this, and then factor out Qij inverse. You'll get this. Now let's put them. So what did we have? We had this, right? Now let's put what we simplified in the equation. So the denominator became this. Also the numerator, we simplified it to be this. Now, interestingly, these two cancel each other, right? Therefore, also, so I bring this in the denominator. I also have this Qij inverse in the denominator. I have minus 2b here. Also have yi minus yj here, right? Also, according to equation 5, the definition of Qij, I can write it. I can replace Qij inverse with this in the denominator. And this is exactly what we had in the equation 13, and we proved that. We proved equation 13. Okay. Here is an example of UMAP embedding. I'm MNIST, I think it is MNIST, digit data set, handwritten digit data set. So we have 10 classes of digits between 0 and 9. And you can see here, these are the labels, and they have been separated in the embedded space, interestingly, very well. So using attractive forces, we have pushed the points in the same classes toward each other, right? And also the dissimilar points away from each other by the repulsive forces. Okay. And let me think. So here, for example, 7. So here, for some, I think if you analyze it carefully, you will see that similar digits should at least fall close to each other. Where is 8 and 0?
From the top left, given right, like below B.
You mean here?
Yeah.
This is 8, right?
Yeah, 0.
This is 8. Where is 0?
That should be to the right. Is it 0?
No. That's not 0. That's actually 1. But 8 and 1 also are related to each other. Why? Because this is 8. This is 8. This is 8. Finally, it becomes like 1. So it's semantic. The space is semantic. You can traverse this space and convert from one digit to another digit. For example, you have 9. You can gradually make it like this, like this. Finally, it becomes like 0. So, or 9, you have 9. You can traverse the space. So gradually, it becomes like 8. Something like that. So you can modify the digits so they become close, similar to each other. And some slides are based on our tutorial paper, Uniform Manifold Approximation and Projection, UMAP and its variants, tutorial and survey. For more information on UMAP, refer to our tutorial paper or the chapter of our textbook. Why? Because I didn't cover everything in UMAP. For example, we have progressive UMAP, where we have with a data stream, with a stream of data where we have incoming data, where we don't have just a batch data. When we have incoming data, we have progressive UMAPs to handle incoming data. Also, let me think. We have neural network based UMAP. They call it parametric UMAP. Whenever we have some algorithm, they make it a neural network version. They usually call it parametric. For example, we have t-SNE, we can have parametric t-SNE. If you use the loss function of t-SNE as the loss function of the neural network, they call it parametric, right? Because you're learning kind of the parameters of the neural network. So we have parametric UMAP as well, and this. Okay, we have covered those in our tutorial paper. We have UMAP library, here it is. And you can go in that and you'll see a lot of examples and how so when you install UMAP, you just go to the Python and it'll say import UMAP, and UMAP, you initialize the class, instantiate the class, and then feed transform, and this is similar to what we have in scikit-learn. Okay, so these are the references. Let's go to the next topic. Hidden Markov model, or HMM. Okay, first off, let's talk about probabilistic graphical models a bit. A probabilistic graphical model, or PGM in short, is a graph-based representation of a complex distribution in the possibly high-dimensional space. So I can say that we have two areas of science, probability and graph theory, right? Probabilistic graphical model is the marriage between these two fields of science. So you kind of combine them. You represent a probability model as a graph, and that's called probabilistic graphical model. Okay. In other words, PGM is a combination of, as I said, graph theory and probability theory. In a PGM, the random variables are represented by nodes or vertices of the graph, right? And there exist edges between two variables which have interaction with one another in terms of probability. If they're related to each other in terms of probability, then we have edges between them. Different conditional probabilities can be represented by a PGM. How? For example, we saw that in also factor analysis. For example, we have Z as a latent variable where X is generated by Z. You can see that X is conditioned on Z, for example, right? So there exist two types of PGM. One of them is Markov network, also called Markov random field. And the other one is Bayesian network. Okay. In Markov network and Bayesian network, so in Markov network, the edges of the graph are undirected. But in Bayesian network, the edges are directed. What do I mean? For example, here, compare these two. This is a Markov network, and this is a Bayesian network. Okay. Consider, now we're going to talk about Markov property. Consider a time series of random variables, right? A sequence, x1 to xn. In general, the joint probability of these random variables can be written in this way. This is called chain rule or multiplication rule in probability. So we have px1 to xn, the joint probability of x1 to xn. I can write it in this way. Px1 times px2 given x1 times px3 given x1 and x2 until the end. P of xn given all of other ones. Okay, so we can write it in this way. The first order Markov property, or sometimes whenever by default when we say Markov property, by default we mean first order. It is an assumption which states that it is an assumption that in a time series of random variables x1 to xn, every random variable is merely only dependent on the latest previous random variable and not the other ones. What? So what do I mean? I have x1, x2, x3, right? x2 only depends on x1. x3 only depends on x2. However, in general, x3 should depend on x1 and x2. But Markov property says x3 forgets x1. Okay. Why does it make sense? This makes sense. Why? Because when we say x2 is dependent on x1, so some information of x1 is kind of hidden in x2. Therefore, x3 can say, okay, the information of x1 is already in x2. Although you have some loss of information, but Markov property ignores that loss, right? So on. So therefore, if we use Markov property, then equation 1 simplifies to this. Sorry, not equation. So you can say P of xi given all of them can be simplified to of P of xi given only the previous one. Okay. Now use this Markov property equation 2 in equation 1. It gives you equation 3. The chain rule is simplified. P of the joint probability of x1 to xn can be written as P of x1 times P of x2 given x1 times P of x3 given x2 until the end. P of xn given xn minus 1, right? The Markov property can be of any order. For example, in a second order Markov property, a random variable is dependent on the latest and one to the latest variables, right? For example, x3 will be only dependent on x1 and x2. x4 will only be dependent on x2 and x3. So we can have second, third order, whatever. A stochastic process which has the Markov property is called Markovian process, right? A stochastic process which has the Markov property is called Markovian process or Markov process. Okay. A Markov chain, now Let's talk about Markov chain. A Markov chain is a probabilistic graphical model which has Markov property. It's called Markov chain. The Markov chain can be either directed or undirected. Okay. So it can be either Bayesian network or Markov network. You shouldn't confuse Markov network and Markov chain. These are different. Okay. Usually Markov chain is a Bayesian network where the edges are directed. Okay. It is important not to confuse Markov chain with Markov network. There are two types of Markov chains. One of them is discrete time Markov chain, or DTMC in short, and continuous time Markov chain, or CTMC in short. As it's obvious from their names, in DTMC, the time of transactions from a random variable to another one is discrete, but in continuous time Markov chain, it's not discrete. What do I mean? For example, an example of discrete time Markov chain is that x1 comes in time 1, x2 comes in time 2, x3 comes in time 3. But in continuous time Markov chain, x1 might come in time 1, x2 might come in time 1.5, x3 might come in time 4. Something like that it might be. So yes, and if the variables in a DTMC are considered as states, okay, then DTMC can be viewed as a finite state machine, FSM, right? Finite state machine or finite state automation, FSA. Finite state machine is very important for people in control theory, because you have a state machine where you go from one state to another one based on some rules. Okay. By the way, we also have the concept named Markov chain Monte Carlo, MCMC. Okay, that's just a method for sampling from distribution. Okay, for more information on MCMC or Markov chain Monte Carlo, see my tutorial named sampling algorithms from survey sampling to Monte Carlo methods, tutorial and literature review. In that, I have explained Markov chain Monte Carlo, which is a method for sampling from the distributions. Okay, let's continue. Hidden Markov model, or HMM in short. So HMM is a DTMC. It is a discrete time Markov chain, which contains a sequence of hidden variables called states, in addition to a sequence of emitted observation symbols or outputs. So what here is an illustration of hidden Markov model. So what do we have? These are states. These are hidden. Why? Assume my eye is here. Assume I'm looking at this from here. This is my eye. Okay. I can't see the hidden states. These are hidden, right? Hence the name hidden Markov model, right? I can't see the states which are hidden, but I can see these. These are called observed variables or emitted variables or observation variables or outputs, whatever you call it. If you consider only one of them, which is not a time series, you saw that in factor analysis, right? We saw that. But now here we have a time series. So it's a Markov chain. We have an observation sequence of length tau. Assume we have a length tau, right? Here it is tau, which is a number of clock times, right? T goes from 1 to tau. Let n be the number of states and m be the number of observation symbols. In this figure, n and m are equal, but not necessarily. Don't need to be necessarily equal to each other. Maybe some hidden states don't emit anything. Some states might emit several things by different probabilities. We show the sets of states and possible observation symbols by this. So this is the sets of the states, S1 to Sn, okay? And we have O1 to OM, we denoted by O. the set of observations. We show being in a state Si, so we are either in one of the states, right? Being in a state Si, we show it by SIT at time t. And being in observation symbol OI at time t by OIT. Okay. Now let the matrix A, which is an n by n matrix, while n is the number of states. An n by n matrix, we call it transition probability matrix, or TPM in short. And what is that? Its ijth element, we denote it by Aij, is the probability of Sj t plus 1 given Sit. What do I mean? The probability that I go from Sit to Sj t plus 1. What do I mean? The probability that at time t I was in Si, but now at time t plus 1 I want to go from Si to Sj. Okay. Obviously, summation of Aij for j from 1 to n should be 1. Why? Because it's probability, and from state Si I can go to several states, right? If I sum over all of the states, the probability should be 1. I can go either to a state, for example, I'm in state 1, I can go to state 2 or 3 or 5, only these 3. Then the summation of these probabilities should be 1, right? There is no other option. So the summation should be 1. Emission probability matrix. We have another matrix. We denote it by B, whose ijth element is denoted by Bij. It's an n by m matrix. N is the number of states. M is the number of observations, right? And what is that? Bij is denoted as this probability of OJT given SIT. It means that the probability that at time t I go from state Si to the observation OJ. What do I mean? I emit. What? No, those are not the states. Those are observations. No, we see. We observe them. S is a hidden state. We can't see them.
So the hidden state are decided upon what?
When we usually is the length of our time series. For example, assume it is action recognition. The states are just the different states that we are doing, right? Yeah, usually it's that. So different observations. We will see some examples. But usually it's determined by the length of the time series that we have. Okay, so Bij, we have Aij, and again, the summation of, so this is the probability of emission. Bij is the probability of emission from Si, emission of Oj, right? And this summation should be 1. Summation of Bij, where j goes from 1 to n, should be 1. Why? Because from Si, I can go to several observations. If I sum over all of the possible observations that I go from Si, then it should be 1. Let the initial state distribution be denoted by the vector pi. Pi is an n-dimensional vector. N is the number of states, P1 to Pn, where Pi is denoted as this probability of Si1. What do I mean by 1? Time 1, initial time. Initially, let the distribution be Pi. And again, summation of Pi for I from 1 to n should be 1, right? To satisfy the probability properties, right? An HMM model is denoted by this tuple. Lambda, which is tuple of pi, A and B. If you give me pi, the initial distribution probability of states, A and B, then you have given me all information for the hidden Markov model, right? Because A, what does A say? The probability of going from one state to another state. What is B? The probability of emission from states to observations. And pi is the initial distribution. Assume that a sequence of states is generated by the HMM according to the TPM. We denote this generated sequence of states by this, right? Assume I'm generating some sequence of states because with every probability another is a different sequence will be generated, right? It's stochastic, it's random. So SG1 to SG tau, where SGT at every t belongs to one of the states, right? The state set of states S. Likewise, a sequence of outputs or observations is generated by the HMM, right? So this is a sequence of states, and this is now a sequence of observations. So I denote it by OG, OG1 until OG tau, where OG at every time t belongs to the set of observations O. Okay, we denote the probability of transition from state SGT to SGT plus 1 by this. This is according to the definition of matrix A. It makes sense, right? A, SGT, and SGT plus 1, right? Why can I write it in this way? Because these are the states in the each row and column of matrix A belongs to the corresponds to one of the states, right? That's why I can write it in this way. And also the initial probability of SGI, I write it in this way, right? As probability of SGI. Okay. Likewise, we denote the probability of SGT emitting the observation of OGT by this, according to the definition of matrix B, right? B of SGT and OGT is the probability of OGT given SGT. So the probability of going from SGT to OGT. Okay. Now we have talked about the fundamentals of HMM. Now let's talk about likelihood and expectation maximization in HMM. According to this figure, the likelihood of occurrence of the state sequence SG and the observation sequence OG, so assume you have some state sequence SG and some specific observation sequence OG, okay? Now, what is its likelihood to happen? The likelihood is the joint probability of SG and OG, right? I can write it in this way. Probability of SG1, so initial probability of states, times probability of next states given previous states, agreed? Times probability of OG given SG. What do I mean? So this is the initial probability of states. Then this kind of denotes the probability of matrix A, which state I go from one state to another state, right? Also, this is the probability of emission, whose responsibility is for matrix B. So this is responsibility of matrix A, this is responsibility of matrix B, and this is responsibility of pi, right? So I can write it in this way, probability of SG1, and this is product of all of these probabilities, probability of SGT plus 1 given SGT, because it's the probability of going from SGT to SGT plus 1. And why am I allowed to multiply them? Because they are independent of each other. Also, I have probability of going from SGT emitting, from SGT OGT, okay? And I multiply them because they are independent again. Then, according to the definition of matrix A and B and pi, I can write it in this way, right? So we have this. This is what we found. I'm repeating it here. Okay. Now, usually we use log likelihood as always, because it makes it simpler. L is the logarithm of the likelihood. Therefore, we have logarithm of the terms. And we know that logarithm of multiplication is the summation of logarithms. Therefore, these multiplications here become summation. Also, these multiplications become summation, and logarithm of product becomes summation of logarithm. Right? So logarithm, when passes through product, becomes summation of logarithm. Now, let 1i be a vector with entry 1 at index I. So what do I mean? 1i is something like this. All of its elements is a vector. All of its elements is 0 except the ith element. Also, let 1 SG1, what does it mean? It means a vector with entry 1 at the index of the first state in the sequence SG. Which state is it, right? At time 1, which state we are in this state sequence? It's that element will be 1 and the rest will be 0 in 1 SG1. For example, if there are 3 possible states and the sequence of length 3, assume we have this sequence, assume. Then 1 SG1 will be this. Why? Because initially we are at the state 2. So the second one should be 1 and the rest should be 0. Right? This is an example. Okay, the terms in this log likelihood are these. So consider the first term. It is here, right? Therefore, as if that's a scalar, let's write it in the vector form. I can write it as 1 SG1 transpose logarithm of pi. What does it do? It filters everything except the SG1's elements. Okay. So also the second term, I'm writing them in vector form. So, or matrix form, vector form, whatever. So we have aij to the power of 1 ii, 1 jj. What does it mean? I can have this multiplication. Always this power is 0. So everything to the power of 0 except 0. Aij is not 0. Aij to the power of 0 becomes 1. So it doesn't have impact in multiplication. Only the term, one term will have effect, and this power becomes 1 in that term, in the term of SGT minus 1 and SGT, right? When we have this power becomes 1, and we'll have aij only for that specific. So whenever I becomes SGT minus 1 and j becomes SGT, this power becomes 1, and the rest of the terms will be to the power of 0, which doesn't have impact in multiplication, right? Therefore, if I take now, I have this term, right? Logarithm of this. Again, this logarithm of multiplication becomes summation of logarithm. So these multiplications become summation. I have logarithm of this term. We know logarithm of a to the power of b becomes b logarithm of a, right? So the power becomes behind logarithm, and then I have logarithm of aij. Okay, interestingly, I can write this in matrix form as this: 1 SGT minus 1 transpose logarithm of matrix A times the vector 1 SGT, right? And what does this mean? Logarithm of matrix. It means that logarithm of every element of the matrix A, applied element wise. Okay, now the last term. This is the last term, right? That we had. So BSG OGT, again, similarly with the same explanation that we talked about, we can write it in this way. It's logarithm, which we have in the third term. Again, similar to before, we can write it as this. Logarithm of product becomes summation of logarithm, and then I can write it in this way. 1 SGT transpose logarithm of matrix B, 1 OGT. So I wrote them in matrix form and vector form. Okay. Hence, the log likelihood that we had, what? Matrix form confuses you? Why?
Because
Okay.
there is this one equation, but for the loss of the differentiator.
Okay.
So before, like in the statistical learning ones, I just like used the whole matrix for X and like whatever we had the parameters. But after the differentiation, the indexing and the row or column wise transposition was so like wrong that in the end I was like, I know it is supposed to be a column matrix. So I just made it a column matrix.
But
Because you remember you told us like whenever you differentiate, this should come out to be
yeah, I always have told you that you can check whether the dimensionalities match with each other. Also, you can check the dimensionality of derivative.
I just checked it.
Yeah.
And of course we made it to be like I just like whenever it was going down or like transpose.
But you don't need to do it forcefully. It can help you analyze whether you're right or wrong. You're right?
Like, I don't know. We haven't done differentiation on matrix. So
Okay. But
that's why I was like, if I transpose this, I get the correct order of things.
yeah, I
Because,
understand.
you're supposed to get like, a row multiplication in bottom. So you get like one bit or like multiple values.
Yeah, I understand. But you should note that why do we usually make it matrix form or vector form? Because we don't want to do for loop. For either on paper or on the computer. Why do we do for loop? Yes, it's not computationally efficient. So let's do it matrix form, vector form. Okay, well, hence we can write. So this is the log likelihood that we have now in matrix form, as we derived, becomes equation 18. Right? Okay, this is what we found. I'm repeating it here. So we have some missing variables. Do you remember the expectation maximization, which we introduced in the lecture of mixture models? What was it? We said when we want to do maximum likelihood estimation, MLE, if we everything is known, then we have log likelihood or likelihood, we maximize it, right? In optimization. However, what if we have some missing data? Then we can't maximize the log likelihood because it has some missing data. Let's first take expectation over of the missing data over the available data. This is the ES step, and in the MS step, we maximize the log likelihood. That's called expectation maximization. The missing variables here in the log likelihood are these. These, we don't know them, right? We don't know them. Why? Because we want to find SG and OG and these things. It's a chicken and egg problem. For finding SG and OG, we need these, but we don't know SG and OG yet. So it's kind of missing the data. Therefore, we use expectation. The expectation of log likelihood with respect to the missing variables is this. So expectation of log likelihood. Expectation is a linear operator, so I can write it in this way, expectation of the terms, and it also passes through the summations because it's a linear operator, right? Okay, so I define this term with expectations. I define it to be Q. I denote it by QPAB. Okay, so equation 19 is I denoted by QAB. Now, MS step in expectation maximization. We maximize this with respect to the variables, optimization variables. What are they? These are unknown, and we want to find them. PI, the initial the states, this probability of initial states, Aij, the elements of matrix A, and Bij, the elements of matrix B. So I maximize this QPAB. And what are these? These are the three things that we saw. So these are pi I, Aij, and Bij. I have three constraints, no, more than three constraints. One constraint here, n constraints here, and n constraints here. So I have 2n plus 1 constraints, right? What is that? We already talked about that the summation of pi I should be 1. Summation of Aij, j from 1 to n should be 1. But I have for each I can do that. Therefore, for all I from 1 to n, I have this constraint. Also for Bij, I have these constraints, right? And now it's an optimization problem. What should we do? It's a constraint optimization problem. Again, as before, consider take the Lagrangian and take the derivative of the Lagrangian, set it to 0, right? So we have Lagrangian. This is the from here until here. So these three terms are Q pi AB, the cost. And now I have these terms for the constraints where eta I, eta 1, eta 2, eta 3 are the dual variables or Lagrange multipliers. Okay, so I'm repeating the Lagrangian here. Now let's take the derivative of Lagrangian with respect to optimization variables. We know that the first term in the Lagrangian, which is this, can be simplified to this. So what is this? First off, I have this inner product. I unroll this inner product to become 1sj1 is first element times logarithm of pi 1 until its tauth element until times logarithm of pi tau, right? And I know expectation is a linear operator, so I can write it in this way. And now one of the optimization variables was pi I, right? So I take the derivative with respect to pi I, and we know that is for a specific I. Therefore, all of other terms are constant, go away, and I will have only this. So what is this? Let me think. So I will have, so consider the ith element of this. It will be derivative of, let me think, this with respect to pi I. So I have logarithm of pi I, which will be 1 over pi I. Am I right? Let me think. Oh yes, I'm 1 over. Give me a second. What was I doing here? I know what I did. So what is this term? Do you know what is this term? This is for the Lagrangian. So here I have this. Also the first term. So by the way, the second term and the third term are constant with respect to pi I. So they go away. These two last terms also are constant with respect to pi I. They go away. I only have these terms, right? The first term, I simplified it in this way. And this term is derivative with respect to pi I becomes minus eta 1 pi I. But I'm thinking about this term. Mm, 1 over pi I. Okay. There might be a mistake here, but there is no time for me right now to find out what the mistake is. Doesn't matter. because of the logarithm of derivative of logarithm of pi I. I'm thinking about it. Doesn't matter. So the only other terms go away, and I only have the term expectation of 1 SGI tau logarithm of 1 SG1 I logarithm of pi I, right? And its derivative becomes this. Here I have some doubt, but doesn't matter. And this term, its derivative is minus eta 1 pi I. If I set it to 0, I rearrange the term. It gives me pi I. Okay. Now I know that the summation of pi I should be 1. According to this equation that I just found, I put it here in this equation in the constraint that I had. So I will have this, right? This is summation, right? I have this, and I know that only one of them is which element? Only one of the elements is 0, because do you remember the definition of 1 SG1? It means that only the SG1th element will be 1 and the rest will be 0. So only that one will be 1 and the rest will be 0. Therefore, it will be 1 over eta 1, and it should be equal to 1, right? Therefore, eta 1 is 1. Now I put eta 1 in equation 22. What does it give me? It gives me equation 24. Pi I equals expectation of 1 SG1 I. Now the other terms. This was the Lagrangian, do you remember? Okay, now we take derivative of Lagrangian with respect to another optimization variable, which is Aij. If we do that, we know that the first term is a constant with respect to Aij. We only have this term. The third term is also a constant with respect to Aij. So the terms which are not constant is the second term and this term. Only these two, right? Okay. Derivative of this with respect to Aij only captures the ijth element of A. The other elements of matrix A are not important. Therefore, it gives me summation of expectation, only the ijth element. 1 SGT I, 1 SGT plus 1 J, right? Do you agree? And also, this term, its derivative is minus eta 2 Aij. If I set it to 0, it gives me this. Again, I want to find this dual variable. I have a constraint, this constraint I had. So I put this equation 25 in the constraint that I had. What happens? Can you tell me? So for the jth element, yes. So on we know that only so here only for the jth element this becomes 1. For the rest will be 0. For the rest will be 0, right? Therefore, it only kind of filters only the jth element. Therefore, only the jth element will appear, and the rest of the elements in this summation becomes 0. Therefore, I will have this. Set it to 0 as we had in the constraint. Set it to 0. Rearrange the terms. Eta 2 is this. Now put eta 2 back in equation 25. It gives you equation 27. I know it's a bit hard to absorb, but these are the parts of machine learning. We are in the last sessions of this course. So these are advanced topics of machine learning. Okay, this is the Lagrangian again. Now we had another optimization variable, and what was that? Bij. So we take derivative of Lagrangian with respect to Bij, set it to 0. Again, likewise, it's very similar to the previous analysis. Only the terms which are not constant with respect to Bij is this term and this term. Only these two terms, right? The first element, so the first one, when we take derivative with respect to Bij, only the ij's elements will be captured. The rest will be constant. And this also gives me a minus eta 3 Bij. Set it to 0, it gives me Bij as this, equation 28, right? But we have a constraint where summation of Bij for j from 1 to n should be 1. If we put this in this constraint, what does it give us? We know that only the jth element will be will be 1, and the rest of the elements will be 0. So it kind of filters the jth element. It should be set to 1, right? Rearrange the terms, it gives you eta 3. Put back eta 3 in equation 28, it gives you equation 30. So we found the optimization variables, right? We've solved the optimization problem using the method of Lagrange multipliers. Okay, let's have a break, come back at 9, and we continue HMM. Again, I understand it was a bit hard, but HMM is hard. It took me a while to understand HMM or myself. Okay, we come back at 9. Okay, so before we continue, I tell you one thing. Here, do you remember in for pi I said on one of them only is 1, and which one is it 1? It's exactly this is the SG1th element. SG1th element. Why? Because this, by definition, one SG1 is SG1th element is 1, and the rest will be 0, right? This signal. Here also, here, I said only one of them is 1 and the rest will be 0. Why? I have this 1 SGT plus 1. I said jth element. I meant, sorry about that. I meant SGT plus 1th element. The rest will be 0. Do you agree? What is this definition of SGT plus 1? We defined that several slides ago. That's a vector whose SGT plus 1 element is 1 and the rest will be 0. Right? This is what we define. Therefore, all of the other terms will be 0 and this is 1. And note that this summation is over j. Why don't I do this for this term? Because I don't have summation over I. I have summation over j. And only one of them will be 0. 1. So here also likewise. Here, which element is it? It's not j. It's OG teeth element. Because of this. And I have summation over j, right? Only one of the OG teeth element is 1 by definition, and the rest will be 0. Okay. And you should note that, did you see that we derived the Lagrange, we wrote the Lagrangian, took derivative, set it to 0, right? I couldn't find a single lecture or a single PDF doing all of these steps. I always, when I was writing this tutorial, I found the final solutions, and maybe some PDFs were only forming the optimization problem. All of these, I derived them by myself. I tried many hours doing reverse engineering these things to find out how did people find these final solutions, equation 24, equation 27, and equation 30. So please know the value of these derivations. You can find these also in my tutorial paper on HMM. One interesting thing, let me tell you, I submitted this HMM tutorial to Archive. Archive rejected me. Can you believe that? Archive rarely rejects papers, but Archive rejected me, and I put it somewhere else. That's fine. That was a funny story of mine. Archive has rejected me for several times. Okay, that's fine. Evaluate what
They don't feel it is valid.
they said. There are a lot of tutorials on HMM. We don't need that anymore. Something like that. Okay. Evaluation in HMM. So far we talked about the optimization of HMM, and now let's talk the evaluation in HMM. What do I mean by evaluation? Kind of test phase, right? Okay, evaluation. It's defined as this. Evaluation in HMM, what does it mean? It means the following. Given the observation sequence OG, OG1 to OG tau, and the HMM model this, lambda, assume pi, A, B, and we found them by optimization that we talked about, right? We found closed form solutions for pi, A, and B. We want to compute this. This is evaluation phase. So given those, we want to compute P of OG given lambda. What is lambda? HMM. Given the HMM model, what is the probability that I get a specific output sequence, OG, right? That is the probability of generated observation sequence. What is the probability of generating this observation sequence? So this is, in summary, this is evaluation in HMM. Given this lambda, the hidden Markov model, what is this probability that I get this specific OG sequence? We can also denote it by this. Denote this by this. Doesn't matter. This probability is sometimes referred to as likelihood. Okay, likelihood in HMM. Assume that the state sequence S1 to S tau has caused the observation sequence OG, right? Hence, we have this. Do you agree? We have probability of OG given SG and lambda as B SG1 OG1 times B SG2 OG2 until B SG tau OG tau. What does it mean? The multiplication of probabilities for emitting outputs from the states. The output OG1 from SG1 in time t1. Then output OG2 from SG2 in time slot 2 until the end, right? On the other hand, the probability of the state sequence, what is that? Of course, it's related to A and also the pi, the initial probability. So I have initial probability of SG1, and also I have these multiplication of A probabilities. Probability of, sorry, this should be, I apologize. Yeah, I think this should be, it's a typo, SG3. This should be SG. So this should be tau -1 and tau, right? So the probabilities of generating from going from one state to the next state in the sequence. Okay, according to the chain rule, what do we have? This is a chain rule. So I have probability of OG and SG given the HMM model. I can write it as probability of OG given SG and hidden Markov model times the probability of SG given the hidden Markov model. So we found these two above. Now I'm using equation 32 and equation 33 inside equation 34. It gives me equation 35, right? And what is that? It's the probability of occurrence of both the observation sequence and the state sequence. So the joint probability of a state sequence and observation sequence. Okay, any state sequence may have caused the observation sequence, right? Therefore, according to the law of total probability, so what do we have? Now I have this joint probability. I want to get rid of this SG. So I can say P of OG given lambda. I can write it as this. Summation of P of OG and SG, where I sum over all of the SGs, possible state sequences. This is called law of total probability. Then I can write it by chain rule according to equation 34 that we had by as this, right? And also according to equation 35, so I'm replacing this with what we found here. Okay, and interestingly here, I can write it as this. So for time slot 1, I have a lot of options, all possible states in time slot 1, right? And this is all possible states in time slot 2. So as you see, multiplication of these summations is kind of all of the permutations possible in the state sequence. This is all of the permutations, right? Okay, which means that we start with first state, then output the first observation, then go to the next state. I'm explaining this. What does it mean? I start with the first state, I output the first observation, then go to the next state. I repeat this procedure until the last state. The summations are over all possible states in this state sequence. Note that I'm talking about a specific observation sequence, OG, but the state sequence can be anything. Okay, direct calculation. This is what we found. The time complexity of this direct calculation, right? This is in the order of O2. This is big O notation. O2 times tau times n to the power of tau. N is the number of the states. Tau is the number of time slots, right? This is the length of the state sequence. So it's very bad. Because why? Because at every time clock t from 1 to tau, there are n possible states to go through, right? So it's very bad. Because of n to the power of tau, this is very inefficient, especially for long sequences. When tau is large, the time complexity blows up. Okay, so rather than direct calculation, we use forward-backward procedure. A more efficient algorithm for evaluation in HMM is forward-backward procedure. What does it do? It includes 2 stages, forward and backward belief propagation stages. So the forward belief propagation, what does it do? Similar to the belief propagation procedure, we define the forward message until time t. The message until time t. What does it mean? I define this. This is called forward message, AI, alpha I t. It means that given the hidden Markov model, what is the probability, joint probability, that at time t, I'm in a state Si, okay? I'm in a state Si, and until now, I have observed all of the observation in the specific observation sequence that I have, right? Until time t, from OG1 until OGT, which is the probability of partial observation sequence until time t, right? And being in a state Si at time t. This is called forward message. Algorithm 2 shows the forward belief propagation from state 1 to the state tau. So let's see forward belief propagation in the forward-backward procedure. What is that? So I have as input, I have the hidden Markov model. What is this? Alpha I1. I say pi I, bi, OG1. So it means that from the state I output the first observation in the observation sequence, and pi I is the state, is a probability of initial probability of the state Si, or the state I, right? And I initialize it for all states. Then for state J from 1 to n, so for all of the states, also for all of the time slots until tau minus 1. What do we have? This is what we use. What does it mean? This is the probability of emitting the jth state in the emitting OGT plus 1 from the jth state, right? At the time t plus 1. Also, what is this? The first, this term. This inside is defined in equation 37. It means that I'm at the probability that I'm at a state Si in the time t, right? Also, I go to the state J from Aij. I go from a state I to a state J. Then probability of this observation can be written as this: summation of alpha I tau. And what was, so we calculated this alpha i's, right? Now we have a bunch of alpha j's or alpha i's here. This is alpha j, but it's dummy variable, right? So you can replace this j by I. Summation of j from 1 to n alpha j tau, right? And then return these for all of the i's, for all of the states, and all of the time slots. Okay. In this algorithm, alpha I is solved inductively. You are using, it's in an induction. The initial forward message is this, right? This is what we saw. What is that? It's the probability of occurrence of the initial state Si, this is pi I, and the observation symbol OG1 from the state I, right? Si. Then the next forward messages are calculated as this. What is that? It's the probability of occurrence of the observation sequence O1 to OT, right? O1 being in a state Si. So why am I saying that? What is the reason for this? Being in observation sequence O1 to OT because of this alpha IT. Do you remember? In alpha IT, we had this. Do you remember? In equation 37. And also being in a state Si according to alpha IT. Right? At time t. Going to a state j at time t plus 1 because of this alpha aij, right? And the observation symbol OGT plus 1 because of this bj OGT plus 1. And what is this summation for? This summation, what is it for? Because at time t, the state SGT, right? The state SGT that we were can be any state. How do we know? How do we know? For example, for this specific observation in the observation sequence, any state can generate that, right? Can generate that observation. Therefore, we need to use the law of total probability. Okay. Finally, using the law of total probability, we have this. Now I'm talking about this line 6. Finally, we have this. What is this? It's the desired probability in the evaluation of HMM. Do you remember? This is exactly evaluation in HMM. So why am I doing that? Because I'm summing over all of the states. So do you see this? What is this? Do you agree that I can probability of OG given lambda, I can write it as probability of OG and SI given lambda, but SI I sum over all of the i's, all of the possible states, right? So I'm kind of here, I'm marginalizing over SI, or I'm marginalizing for OG, and I'm summing over all of the SI's. This is called law of total probability. And interestingly, this is alpha I tau. Okay. Now the backward belief propagation. So we have forward, which we talked about. Now backward. Again, similar to belief propagation procedure, we define backward message. How? Since time tau to t plus 1. So we go back. So we go forward in the sequence, and now we go back. What does it do? What is it? We define this. Beta IT, we define it as backward message. It's the probability of, I have these observations. What is that? Observations of t plus 1, t plus 2 until end. So in the forward message, I have the observation from initial observation until t, but here I have observation from t plus 1 until end. Given that at time t, I am in a state Si and lambda. Note that in forward procedure, in forward message, this term was behind condition. But in backward message, this term is after condition. It's conditioned on. Okay. And this is the backward belief propagation. So I have the hidden Markov model. I initial beta I taus for all i's to 1. Then I have this for loop of states. I have time t from tau minus 1 to 1 because it's backward. I calculate this. I think I have explained it here. So in this algorithm, the initial backward message is this, right? The next backward messages are calculated in this way. This is exactly line 5 of the algorithm. What is that? It's the probability of being in a state Si at time t, going to state J at time t plus 1, and the observation symbol this. Let's see why. What is Aij? Going from Si t to Sj t plus 1. This is exactly, this is responsible for this. And what is B? What is Bj OGT plus 1? It means that from Sj, I emit the observation OGT plus 1. So this is exactly here. So this is responsible for this. And the probability of being in a state Si at time t. Give me a second. Yes, because of this. Because I go from Si to Sj, right? Okay, and this summation is because at time t plus 1, the state Sgt plus 1 can be any state. Can be any, I have the observation sequence, but a state sequence can be anything, right? Can be any state. So we should use the law of total probability. It is noteworthy that for very long sequences, the alpha I and beta become extremely small, right? Similar to the problem of gradient vanishing in deep learning, recursively, right? Because when you multiply very small numbers by each other, they become too small. Hence, some people normalize them at every iteration. So we have this normalization. If we normalize them, then what happens? They must sum to 1, right? So they sum to 1. However, note that if this normalization is done, we will have this. This probability of OG given lambda will be 1. Okay. Now, estimation in HMM. These are different tasks in hidden Markov model. Okay. I know this is hard to absorb. You need to go through this video several times to understand everything. Estimation in HMM. So estimation in HMM means that the previous one was evaluation. This is estimation. Means that given the observation sequence and the hidden Markov model, we want to compute or estimate this probability. What is this probability? Probability of a state sequence given the unobservation sequence. So it's the other way around. Evaluation said, what is the probability of OG? Now here we say, what is the probability of SG given OG, right? So this measures the probability of a state sequence. The evaluation measured the probability of observation sequence. Okay. In other words, I have some observation sequence. What state sequence must have generated this? Let the probability of being in a state Si at time t given the observation of OG and hidden Markov model be this. So I'm denoting this probability as gamma IT, right? And gamma IT times this probability. So I'm replacing gamma IT with the definition times this probability. What is this? According to this chain rule, according to the chain rule, I can write this as probability of Si and OG and lambda, right? The joint probability, right? Also, let's see. Now I'm here. Its explanation is here. I have alpha I, consider alpha IT, beta IT. According to equations 37 and 41, which we found for alpha and beta, okay? This is alpha, right? This is definition of alpha. This is definition of beta that we had. Okay. If you multiply these two by chain rule, it becomes the probability of the joint of them. Then it basically means, what is this? This is the observation sequence. You can say that this is probability of observation sequence and being at the state Si at time t and the hidden Markov model. Therefore, you can write this as this. We just, right? Now, what do we have? Rearrange the terms. So bring this in the denominator. You will get this, gamma I this. and I can change this to this. I can rename it to this, right? What is probability of OG given lambda? It's exactly summation of alpha JT BJT, which is this, right? For all of J's, for all of possible J's. This B also can be analyzed, interpreted in this way. It is because of the forward-backward procedure, which states that the belief over a variable as a product of the forward and backward messages. This is what is this sentence saying? This is in belief propagation in probability theory. When you have forward and backward message passing, the belief or a probability over a variable in a graph, probabilistic graphical model, you can see it as a multiplication of forward message and backward message. Okay. And this is a greedy approach. Okay, this what we talked about here for the estimation. This is a greedy approach for estimation. In the greedy approach, at every time t, we select a state with maximum probability of occurrence without considering the other states in the sequence. This is, have you passed an algorithm course? In algorithm, one of the techniques for algorithm is greedy approach, greedy algorithm. What is a greedy algorithm? A greedy algorithm doesn't care about that. If I want to find the best solution for an algorithm, the best path or the best solution, it might be very time-consuming resource computing. It's very hard. Let's relax the problem, saying that rather than finding the best thing, let me find the best thing for my current step. My current step. Hopefully, local best, if you aggregate them, finally it's almost approximates the global best. Hopefully. It might not, but hopefully. This is greedy approach, because at every iteration you are greedy. Okay, here we are doing this exactly. Here we are saying that which state maximizes this gamma IT? What was gamma IT? The probability equation 47. Probability of SI given OG, right? Which state maximizes this? Take that. Take that. Okay, at every time, at every time. Now another algorithm for estimation. The one algorithm was greedy approach. Another one is Viterbi algorithm, one of the most important algorithms for hidden Markov model, right? Viterbi algorithm. If you have passed any telecommunication course, they also talk about Viterbi algorithm. The greedy approach does not optimize over the whole path, as I said, but greedily chooses the best state at every time step. Another approach to find the best state sequence, which has the highest probability of occurrence. Okay, what is that? Which is maximizing this. It's the Viterbi algorithm. It was proposed in 1967, and Viterbi, proposed by Viterbi, and Viterbi patented that. Okay, it can be used to find this path of states. Different works, such as this reference, have worked on using Viterbi algorithm for HMM. This algorithm 4 shows the Viterbi algorithm for estimation in HMM. So what is that? Here we have the input, the hidden Markov model. We initialize these. Okay, we initialize these variables. We'll explain the algorithm in next slides, but just take a look at the algorithm for now. Then we have some recursion. These 4 states from j from 1 to n, then time from 2 to tau, and I have these. Now I update delta j and psi j. We'll see them. Okay, then I have termination, gives me p star s star. Then I have backtracking, which we'll see, s star, and then equation 16 gives me this probability, and I return it. Right? So let's see. In this algorithm, we have the variable, is it the delta, right? Delta JT. What is delta JT? I define it as this. Maximum of this, delta IT minus 1, so as you see, it's recursive, right? AIJ, right? What is AIJ? The probability of going from SI to SJ, right? And I have this. What is BJ? OGT, probability of emitting OGT from SJ at time t, right? And I'm saying that which state maximizes this? The maximum of that, then times this. Okay. Which is similar to alpha j. Do you remember? Alpha j in equation 39, we found it. I'm repeating it here. This is what we found. So compare these two, it's very similar. Except that alpha jt in the forward leaf propagation uses sum product algorithm here. Do you see? Here we have sum, and here we have product. As we have sum and product, it's called sum product algorithm. But in Viterbi algorithm, we have max product algorithm. Why? Because we have here maximum, and we have product here. These are important algorithms in probability theory: sum product, max product. Okay. Similar to equation 38. So this is equation 38 that we had before. I'm repeating it here. Okay. The initial delta JT, we define it to be this. Delta JT, we defined it in previous slide. Initial, let it be this. Right. Now we define the index maximizing equation 51. What is that? This index. Do you remember? Which state maximizes that? Let's define it to be psi j. So argmax of that, I define it to be psi j, right? I mean this argmax of this, let it be psi jt. Okay. Then a backward analysis is done, starting from the end of a state sequence. So I have these starting from the end. Tau is the end of the sequence, right? So maximize this delta I tau, which a state SI maximizes this delta I, right? Then I say, so which state maximizes that? I call it this star tau at that time. And what is the maximum value of delta I tau? Using that as a star. I call it P star, right? So P star is the maximum value, S star is the argmax. And then we do it recursively. We call it backtracking. We backtrack it. So we start from the end and then we backtrack it using this equation. Okay. So by the way, why is this true? What was psi? This is the definition of psi, right? Compare these two. And you will understand. It makes sense why equation 56, because psi is in essence of a state, right? Which state maximizes that, right? Therefore, we pass this to become the state. Okay, and now these states, S star 1 to S star tau, are the desired state sequence in the estimation. Therefore, the states in the state sequence are maximizing the forward leaf propagation in a max product setting. Why? Because we have max and product. And it is not greedy. It is a global optimum. The probability of this path of the states with maximum probability of occurrence is this, right? P star. So what was P star? This is the P star, right? This is the probability. And note that the Viterbi algorithm can be visualized using a trellis structure. You can see the appendix A in reference 16, or let me Google it. Trellis Viterbi. I want to show it to you. Images. Yes, here it is. Do you see this? No, it went. Sorry, it went to the other. Okay. Can you see my cursor? This is the trellis structure. They visualize Viterbi algorithm using this. As you see, it's considering all of the possible paths. That's why I said it's global. It's not greedy. It's considering all of the possible paths. Interesting. Okay. Let's continue. So, training the HMM. Now, note that so far we assume that we have the hidden Markov model, right? For example, we have OG, let's estimate ST. We have ST, let's find the OG, evaluate OG, right? Now let's train it. Training HMM means the following. Given the observation sequence OG, we want to adjust the HMM model parameters, pi, A, and B, in order to maximize the probability of that observation sequence. So I have some observation sequence. What parameters of A, B, and pi can maximize this probability of occurrence, observation, right? Which hidden Markov model, which lambda maximizes this? Okay, we can solve. So this is equation 58 that we had. I'm repeating it here. We can solve it using maximum likelihood estimation. Of course, we want to maximize this likelihood, right? Using expectation maximization. I did expectation maximization. I found some formulas for that, right? Now we are going to use them. We are going to use those formulas here. One of the algorithms for training HMM is called Baum-Welch algorithm, proposed in 1970. Baum-Welch algorithm. That is the most important algorithm for hidden Markov model. So it is the most well-known method for training HMM. There are other algorithms for training HMM as well. This is the most well-known. It makes use of the expectation maximization results. We define the probability of occurrence of a path being in the states Si and Sj at time t and t+1 as this. So this is called zeta, right? Zeta ijt. I define it to be this: probability of being at Si in time t and Sj in time t+1 given the OG, the observation sequence, and lambda hidden Markov model, right? So we can say this. I have this, I also multiply it by this term. So I have this that I had, I multiplied by this term. Then, according to the chain rule, this becomes a joint probability of them, right? This is chain rule in probability. Then, this B, we want to see why it is equal to this. Let's prove it. Why? Here. In the next slide, I'm proving that. Here, I'm proving this. Because what is alpha IT? Do you remember? We had these equations. I'm repeating them. Alpha IT is probability of observation until time t and being at Si in time t given the hidden Markov model. What is Aij? Probability of going from Si to Sj from at time t to t+1. Bj Og t+1 is this probability of emitting Og from Sj at time t+1. What is the beta j t+1? We had it. It's the probability of all of the observations from t+2 until tau, given that at time t+1 we are in Sj and hidden Markov model and the hidden Markov model. Now, if you multiply all of these terms, this is exactly what we want. This is joint probability, right? Okay. Let's go back. So we had this. We have this equal to this. Rearrange the terms. You will get this. And you can write this probability of Og given lambda as this summation in the denominator. Right? What is it doing? It's basically the numerator, but summing over everything. So it sums to 1. And what happens now? So note that summation of zeta ijt for all of I and j's becomes 1, because summation is everything, all of the possible cases, right? Also note that this probability of Og given lambda in equation 60, where is that? Here is equation 60, right? This POG given lambda, where is that? Here in the denominator. can be obtained from either the denominator of equation 61, which we have it here. Okay, we can either do this, or we can use line 6 in algorithm 2. That is equations 4D. You don't need to go and see algorithm 2 again. I have brought line 6 of algorithm 2 here. It's here. So there are two ways to calculate POG given lambda, either as done in equation 61, or you can use this equation, which appeared in line 6 of algorithm 2 or equation 4D. Right? It's summation of alpha I top. Now, so this is what we found, zeta ij, right? The terms alpha I t, a I j t, b j o g t plus 1, and b j t plus 1, they stand for all of these probabilities that we talked. Probability of the first t observations ending in a state si at time t. So what is alpha I t? Probability of first t observations ending in a state si at time t. What is aijt? Probability of transitioning from a state si at time t to a state sj at time t plus 1. What is bjogt plus 1? Is the probability of observing ogt plus 1 from a state sj at time t plus 1. What is bj t plus 1? Is the probability of the remainder of the observation sequence. Remainder, right? Now I think you understand why we need two directions, forward and backward. Because we are in the middle of the sequence. Once we need to be before that, once we need to after that for observation. Okay. Now recall equations 24, 27, and 30 from EM algorithm. Now I'm going to use them. Do you remember these? 3 equations that we found in expectation maximization several minutes ago, right? So on the other hand, recall equations 47 and 59. So we had these gamma I t and zeta I j t, right? Therefore, if you compare these, you can see that I can say, so this, I can say expectation of 1 SG1I equals gamma I1. Why? Can you say that? Can you tell me why? Why can I write this gamma I1 as this? What does this mean? Gamma IT according to this equation. Gamma I1 means that I want to be in S1 at time t. Therefore, I can say expectation of 1 SG1I, right? The ith element. Exactly. Because according to the definition of 1 SG1, I can also write it for time t. So this is for time 1, this is for time t. For zeta ij, I can also write it in this ways. So I'm writing them in vector form. Also for gamma it, I can write it in this. So I just replace these with what I have in these equations. Now use these inside the results of expectation maximization. You will get this. So use these 4 equations, 62 to 65, in the 3 above equations. Right? Then, I mean, yes. Then you will see that you can replace these expectations that you have with the gamma i's and zeta ij's that we have. Therefore, interestingly, pi I becomes gamma I1. According to equation 47, which was the definition of pi, the correlation of gamma, we have this probability of SG1 at time 1 equals SI given OG, right? Also, I have AIJ and BIJ, these terms, right? These equations were the equations that I could find in the internet. You can see how hard it was for me to do all of the optimization steps to find out how people found out these equations, right? Okay, so we found this Bij with change of variable. We have this. So these are dummy variables, right? I and j. I can write as j and k. So the algorithm is shown here. Algorithm of Baum-Welch algorithm, right? in algorithm 5. Here it is. In this algorithm, what are we doing? In the initial probabilities of being in a state Si at time t equals 1 is according to equation 66. So here we had this. Where is equation 66? Here it is. Right? This is the equation. So we are using that. Now that we derived all of the equations, let's see how they are used in the algorithm, Baum-Welch algorithm. So this is line 2. Then for a state I from 1 to n, and for a state j from 1 to n, this is the equation of aij that we found, right? Also, this is the equation of bjk that we found. Do you agree? This is what we found. Yeah, bjk is according to equation 68. aij is according to equation 67. And likewise, so by the way, according to the count expected number of transitions, oh, you can interpret this in this way, in this equation aij. It can be interpreted as a ratio of expected number of transitions from a state Si to Sj over the expected number of transitions out of a state Si. Do you agree? What is the probability, definitional probability, when you count? You say the probability of occurring something is that how many times this has occurred over the number of all of the occurrences, possible occurrences. You can interpret this equation in this way. It's the number of expected number of transitions from a state Si to Sj, a specific Sj, over what is the denominator, going from Si to anything, to all states, right? Interesting. And likewise, this bjk can be interpreted as this. bjk can be interpreted as a ratio of expected number of times being in a state Sj and seeing observation OK over the expected number of times being in a state Sj. So denominator says the number of times that I'm in state Sj, numerator is more restricted. I'm in the state Sj, but I also see observation OK. Right? Interesting. Very interesting. It's very interesting that I want to dance. Okay, so now normalization. So did we talk about it? Yeah. So we also normalize them for computer error corrections, right? After we find these, we might have some computer error corrections where they need to sum to 1. Therefore, let's normalize them in equations in lines 10, 11, and 12, right? And then we return these. These are the elements of A, B, and pi, right? And then we return these. So this is a Baum-Welch algorithm. For calculating equation the 68, which we had this, we use equation 49. We had this. I'm repeating them. We had this, right? And what is alpha j and alpha beta, alpha I, beta I? Well, we can calculate them using equations 69 and 70, which we had before. It was, yeah, we had all of these equations before. I'm just repeating them. Okay. And now applications of HMM. So we talked about training HMM. We talked about evaluation HMM. We talked about estimation in HMM. Now applications of HMM. Assume we have, I think this answers your question now. So I'm talking about 2 applications of HMM at least. Application in the speech recognition. Before, LSTM was very used widely for speech recognition, LSTM and recurrent neural network, RNN. Before that, the dominant method for speech recognition was hidden Markov model. Okay, before neural networks, hidden Markov model was dominant in that area. So assume we have a dictionary of words consisting of the cardinality of W words. Okay, then for every word indexed by W, so for every word, and this W can be 1, 2. This W is the index of the word in the dictionary. Okay, we have W training instances. So assume for every word I have several training instances. What do I mean? For example, the word hello, 100 people have said hello, and I have recorded that. Hello with English, a British accent, hello with American accent, hello with Scottish accent, different accents, right? So I have several training instances spoken by one or several people. One person can say it in different accents, right? Doesn't matter. The training instances for a word are indexed by Q. So Q is the training instance for the specific word. Every training instance is a sequence of observation symbols obtained from formants. You can divide, so when you say a word, you can divide it into several parts of speech. They are called formants, okay? And so you can define every training instance, every piece of speech as a sequence of the formants, right? We consider an HMM model for every word in the dictionary. So if I have 1,000 words, I will have 1,000 hidden Markov models, right? Training the hidden Markov models are as these, based on references 7 and 8. For every word, WI, consider the training sequences OWG indexed by Q. What do I mean? These are the training instances, right? I told you. So for every word, I have several training instances, and let index by Q, that is this, right? OG1 until OGQ W. And what is this? What is OG1? Can you tell me? It is one of the training instances that I have. For example, this is hello. OG2 is hello. OG3 is hello. OG4 is hello. Different hello with different lengths, with different accents, right? So observation, every observation here is one of these samples of a speech for hello, for example, right? Train the hidden Markov model for the Wth word using algorithm 6 to obtain lambda W. What is the algorithm 6? Baum-Welch algorithm for training HMM. So for every word, we train one HMM. Interesting. And then in the test phase, for unknown test word, now you so we have trained HMM for all of the words in the dictionary. Now a piece of speech comes as the word, right? I want to estimate what word it is. A speech recognition, right? We want to recognize the speech. So with sequence this, what is this? Just give me a second. Give me a second to think. That's it. For word are indexed by Q. That's correct. Yes. Okay. Oh, I get it. So we recognize the word as this. So we calculate this. What is that? Probability of OTG given the hidden Markov model. What does it mean? Can you tell me? The probability that this is the word hello, the probability that this is the word hi, the probability that this is the word bye, the probability that this is the word I. Am I right? For every word, I can calculate the probability. For all of the words in the dictionary, using the forward belief propagation. Then the test word is the one which maximizes this probability. Which one maximizes the probability of generation of that word? Do you agree? And so the test word is recognized as the Wth word in the dictionary. Interesting. In the test phase of speech recognition, usually the Viterbi algorithm is used. So what do we do? Hence, another approach for recognition of the test word OTG is this. So that was one of the approaches for test phase. Another approach is that we calculate probability of OTG and SGT given in the hidden Markov model. The previous approach used calculated the probability of OTG given hidden Markov model. Here, let's calculate the joint probability of OTG and STG given lambda. And it was done by Viterbi algorithm. Do you agree? For all of the words using the Viterbi algorithm, which was algorithm 4, then the test word maximizes this probability. Right? Note that the words are pronounced with different lengths, fast and slowly. But why is hidden Markov model? Why was it dominant in speech recognition? Why was it very good to use? Exactly. So it adapts itself to the length. It's robust to the different lengths, right? It determines how many states do I need. So with different lengths by different people, HMM is robust to different repetitions of the states also repetitions of the states, right? So when I say hello very fast, then maybe for e, for l, for o, I have 4 states. But when I say hello, maybe I have 3 he, 2 e, 5 le, and 2 o's, right? Because I spread that in time. And HMM is robust to the repetitions of states. It doesn't matter whether you have 3 he or 1 he. That's the same. Interesting. Another application is action recognition. That was used in my master's thesis. Okay. Fisher poses. That was the paper that we worked on. And what did we do? We had different states of actions. For example, for jogging, this is one state, this is one state. And when you have you repeat it, it becomes jogging. Or this is one action, and this is one action, and the states are these. And we use the Kinect sensor for finding the joints, right? So we found the joints for each state. Then we classified them by linear discriminant analysis. Equivalently, we projected the states into Fisher discriminant analysis, and then we use the Euclidean distance for classification. We talked about it. FDA with Euclidean distance is equivalent to LDA. So we call that Fisher poses. And then after recognition of the states, we fed them to hidden Markov model for finding out which action it is. Therefore, for every action in the data set, we trained one hidden Markov model, right? So here, assume we have a set of actions, W, and for a sequence of observation symbols we call poses, right? Different poses, and HMM is trained for every action. And training and testing HMMs for action recognition is the same as training and test phases explained for speech recognition. Then again, it's robust to different sequence lengths because people do the actions with different pacing. Maybe this is also jogging, and this is also jogging, right? And as it is robust to different repetitions of the states, then it's good. For more information, you can see my thesis and paper. The thesis is in Persian. You can find it in the library of Sharif University, but the paper has been published. Search Fisher poses and you will see that. Okay, an example is this: action sit, action stand, action turn. For example, action sit, we have several states: stand, and then sit, right? We have action, or we can have also for action stand, we have poses sit, and then poses stand. For action turn, maybe we have a stand, and then tilt, right? So the actions are sequences of poses, and we have different lengths of or pacing. By the way, some states are between the states. For example, this is sit, this is a stand. This is between the sit and stand. We using Fisher discriminant analysis, we see which one is closer. This is closer to a stand, this is closer to sit. So we can find out, classify them, right? And therefore, they are also generalizable. You can see Fisher poses for human action recognition using Kinect sensor data. This is our paper published in 2017. Okay. And this is an example of different data sets of, for example, different actions, right? In different time slots for train and test. Interestingly, for example, test instances are never existing in the training set, but we can still recognize them. So it's generalizable. Acknowledgement, some slides are based on our tutorial paper, Hidden Markov Model tutorial. For more information, you can see my tutorial paper. There are other things in the tutorial paper which we didn't cover. For example, relation of hidden Markov model with factor graphs. Some slides are inspired by the teachings of Professor Mehdi Molkarai and Professor Kevin Granville and Professor Mujou, all of them at the University of Waterloo Department of Statistics. HMM, interestingly, exists in scikit-learn. You can use HMM in scikit-learn. Okay, and these are the references. Okay, and this is our paper that I talked to. Okay, so thank you very much for attending, for listening. This was the last session of lecturing. The next week, this time, is the time of presentation, right? So groups will present here. And I will make an announcement. I will ask you guys I will ask which whether teams can come sooner or not. I can come at 6. Can start at 6 because if we start at 6, I think we can finish at 11. No, the last lecture of the semester for the course, but the last lecture of me teaching was today. Okay. But for deep learning, we still have Tuesday. The Tuesday after that will be the last lecture. Okay. Any question before we conclude the course? Okay, if there's one more thing, I couldn't cover some topics such as clustering. There was no time, but I think I tried to cover the things which you could hardly find in other things. For example, you can easily find out what k-means is. By just one Google and k-means, you can learn it in 5 minutes. But you couldn't easily learn hidden Markov model. That's the reason that I tried to cover hidden Markov model rather than clustering. Okay. Sure. Great. Did you enjoy it, by the way? Enjoy the course? Was it good? Okay. Okay, great. Thank you. Thank you very much.